All right, in the last example, we were given a formula and we were asked to find the maximum value. Now, a lot of these examples are not going to give you a formula. You have to write the formula, which is what makes some of these optimization problems hard. So you just need to take it step by step. There's a lot of steps to some of these problems. So let's take a look at example 2. In this example, the farmer wants to build a rectangular pen against a long straight wall enclosing 128 square feet. And so we're asked to find the minimum length of fencing required. All right, now I'm going to start by just drawing a picture. Okay, so here's my wall. All right, I'll make it look here. Here's our wall. This is the wall. And then we're going to build a rectangular enclosure. So I'm just going to draw a rectangle up against this wall. Okay, so that we can have something to refer back to. Okay, so now we want this rectangular area to be 128 square feet. So 128 square feet. That's what we want the area to be. And we want to know what's the minimum length of fencing, right? Now the fencing goes along these edges, right? It goes along, we have 3 sides because we're using the wall as one side of the pen. And so I'm going to call this X and I'm going to call this X and we'll call this length of fencing Y, right? It's a rectangle. So these opposite sides have to be the same. All right, so I have a picture now. I've assigned some variables so that I can work. Okay, we can do some math now. We have some variables. Now, there's a constraint on the area, right? This is the constraint. Let me write that down. Constraint. Our constraint is on the area. We want the area to be, area to be 128 square feet, right? Now, given the variables that I've assigned, the area is just length times width. So x times y is our area. And I'm going to set that equal to 128 square feet, right? That's the units, but and then, so that's my constraint equation. And what I'm trying to do is minimize the amount of fencing. So I want to minimize. Well, I'm going to call this the objective, right? Because this is what I'm trying to do. This is my objective. My objective is to minimize the length of fencing. Okay, so I'm going to call that f, the length of fencing f, right? And this is the function that I'm going to find the minimum of. All right, this is what I'm trying to minimize. Now, given the dimensions that I have here, x, it's essentially x by y, an x by y rectangle. So, and the fencing is going to go around the perimeter, except for the back side is a wall, so we don't need fencing there. So the amount of fencing we need is 2 lengths of x, right? 2 lengths of x, which is 2x, and then plus the length of y. That's our objective, right? So this is our objective function. All right, so now that we have a formula, right? I have a formula for the length of fencing, right? I want to find the minimum of it. So I'd like to be able to take the derivative, set it equal to 0, and do everything that I've done in the past to find the minimum of a function. And but right now I've got too many variables. Okay, right? I've got x and y. Right? If I want one variable, and that's where the constraint equation is going to come in. I can solve for y in terms of x or x in terms of y, but I'm just going to go ahead and solve for x or for y in terms of x. Okay, so I'm going to say y is equal to 128 over x, right? If I just divide both sides by x. And now I have a relationship between x and y, and I can replace the y in this formula down here. So I have 2x plus 128 over x. Okay, so that is my objective function now written in terms of only x. All right, I had to eliminate that variable. All right. So now that we have a formula for the objective function, all we need to do is find the derivative. Why did I write? Hang on. I gotta why did I write that? Okay, this is just a rewrite of the formula for the fencing. I just eliminated the variable. Okay, so now I want to take the derivative, set it equal to 0, and find the critical points, and then evaluate the critical points and everything like I've done before, right? So I'm going to come over here because I want to, I'm going to, let's see, because I know I'm going to run out of room. I got to use the space over here. So I'm going to find f prime of x, right? F prime of x. Now, this is just the same as 2x plus 128 x to the minus 1. Running out of room over there, but and so that'll help me when I find the derivative. Right, so I can just use the power rule on it. And so the derivative is going to be 2 minus 128 x to the minus 2, right? That's the derivative. And so I want to find the maximum of f. So I'm going to take the derivative, set it equal to 0, get the critical points. So now this 128 x to the minus 2 is just the same thing as 128 over x squared. And I'm just going to add that to both sides. So I get 2 equals 128 over x squared. Multiply both sides by x squared and then divide by 2. So I'm going to get x squared is equal to 64, which means that x is equal to either 8 or minus 8, right? You get two answers. But then we have to think about the practical, this practical problem. X represents the length of fencing, and I don't know how to go out and buy a negative length of fencing. So I'm gonna eliminate that one. I'm gonna consider it outside the domain of the fencing function because I really need to buy positive lengths of fencing. All right, so this is my critical point. So I have a critical point at x equals 8. All right. Now, I would like that to be a minimum, right? There's only one, so let's hope it's a minimum. But we got to test it. So with this one, it's pretty easy just to find the second derivative here, right? We'll find the second derivative. Actually, let's find the second derivative. And then, okay, so the derivative of 2 is just 0. And then if I bring down the 2 or the negative 2, I get a positive 256x to the minus 3. Okay. Now when I look at that, I've got a positive 256. If I raise, this is the same thing as 256 over x cubed, right? When I cube a positive number, I get a positive number. So I know that this is greater than 0 if x is greater than 0, right? Which I want x to be greater than 0, right? Because I want positive fencing lengths. X represents the length of one of the sides of this rectangular enclosure. All right, so that tells me that the second derivative is concave up for x greater than 0, which, concave up looks like that. So I have a local minimum at x equals 8, right? Because that's a positive value of x. All right, now we're getting there. Now we've verified that that is a local minimum. So what do we need to go back up to the original question and figure out what it was that we were asked for. We weren't asked for just one of the side lengths. We were asked what is the minimum length of fencing required. So if I'm going to go to the store, I got to buy some fencing. I want to know how much to ask for, right? So I want the total length of fencing. So let's go back over here to our fencing function. All right, our fencing function was 2x plus y. Now, we could find y, right? If we wanted the dimensions, y is just 128 over 8. So we could find y. What do we get when we divide 128? Does get 16. 16, okay? All right, so basically we want to build an enclosure that's 8 feet by 16 feet. All right, so the total length of fencing, so the total length of fencing is going to be 2 times 8 plus 16. So we get 32 feet. Okay, so so we can answer the question now. The minimum length of fencing required. Minimum length of fencing required is 32 feet. 32 feet. Okay, now my work kind of goes all over the place here. I found the formula, I took the derivative, and then I had to come back up here, and so my work is a little all over the place, but that's my final answer, is that the minimum length of fencing required is 32 feet. All right. So let me just show you this next box. There's some general guidelines for optimization problems. We want to read it carefully. We want to identify the variables. Oftentimes it's a good idea to draw a picture, which we did, right? We want to identify the objective function, right? That's the function that we're trying to maximize or minimize. And identify the constraints, right? And write them in, write those equations in terms of the variables that we assigned. And then we want to use the constraint to eliminate all but one of the variables in the objective function. The objective function, remember, is the function that we're trying to minimize or maximize. Okay, so once we have the objective function written in terms of one variable, then we can just take the derivative, set it equal to 0, find the critical points, evaluate the critical points, just like we've done in these past sections where we're finding local minimum or maximums, right? So, and you need to test it. Just make sure you use calculus to test to make sure that you have the minimum or maximum of the function. You can use either the first or second derivative test, or if you have a bounded function, you can check the find the local minimum, maximum, and then check the endpoints as well. All right, so that's the basic process. Some of these problems get a little bit tricky, but that's the basic process. So I'll meet you in the next video for the next example.